Yes, sir, we can hear you.
Okay, so I guess you were not aware of this session, right?
Yes, sir, it was not there in the calendar.
Oh, okay, okay. Sorry for that. Yes, somehow we have missed that. Okay, so today's we'll be discussing regarding the week 8. So this is a open session for week 8. So I'll be going through each and most of the topics, okay, which are important from the week 8. And if you are having any doubt, you can ask me. Okay, I'll start now. Because we are having 4 or 5 students only. So, like all of you have seen the lectures, like week 8 content. You can unmute yourself and you can say if you want to. Any of you? Are you able to hear me? Any of you can say something or?
Hello, sir.
Yeah. So yeah. So have you went through the lectures like week 8 content?
No, sir. No, sir. I have not gone through the lectures.
Okay. So okay, I'll try to like bind. I'll try to I'll try to what you can say explain some of the important topics of week 8, right?
Yes, sir.
So
Yes.
that
Yeah.
it will help you all. So okay, so I'll go through that and then I'll solve some of the examples.
Okay, sir.
Okay, so I'll go through the same slide that our professor has used. Okay, so if you are having any of you are having any doubt at any point, you can ask me. Okay. Are you able to see the screen?
Yes, sir. Yes, sir. We can see that.
So in this week, what we are discussing, like in the first lectures, like here we are in this whole week, we are just calculating the parameter for the samples. Okay, so there are many methods with like by which we can calculate the parameter of the particular distribution. Okay, like there many times what happens, we have been given some stats, like we have been given some sort of data, like okay, and many a times just we know regarding the distribution. Okay, we don't know the all the parameter, like what's the mean for this distribution and variance of this distribution from where we are getting the data, sort of things. So whenever we have to conclude to some results, so whenever we are concluding with some results, so we have to be we should have some of the data so that we can rely on those final results. Okay, so if we are giving some sort of final result, then we should be having some sort of data, some sort of things so that we can tell that guy, okay, this is what we have got from the data and this is our final conclusion. Okay, so that it otherwise any from the sort of data whatever we are having, anyone can say, okay, okay, this is the mean or whatever, like the things they have been asked. Okay, without any sort of data, but that is not correct. Okay, so what happened in like most of like in the next you'll be going through the stats and all, many of the data if you are having, so you should be having some sort of information or some sort of conclusion. If you are doing, you should be back with some of the data so that you can support your final conclusion. Okay, so what happened, we are having so here we'll be going through some of the methods so that we can calculate our parameter. Like for example, if we are having some sort of like equation. Okay, so if I'm having some sort of we know okay, this is a Bernoulli distribution trial. Okay, but we don't know the p value. Okay, if we are not knowing the p value, but this distribution we are knowing this is a Bernoulli, and out of this Bernoulli distribution we are taking out some of the samples. Okay, this was the sum of this was the sample. Okay, from those samples, if we have to calculate, or if we have to not exactly calculate, but we have to somehow estimate the value of that parameter. Okay, so we are having many of the methods that we'll be discussing in further, like in some time. Okay, so here, what is that? So if we have been given some sort of, this is the first example I'm giving. This has been discussed in the lecture also, but I'll try to make it even simpler. Okay. So here P was the parameter of the distribution. Okay, that was, if that has been not been given. Okay, so that we have to estimate. Okay, right. So we can have some sort of parameter estimation things. Okay, we can have the parameter estimation things. So okay, so like for example, in the Bernoulli, we have to estimate the parameter like P here, because here only the P was the parameter, right? Here P only P was the parameter. Like for example, if I'm having normal distribution, so in normal distribution, we'll be having nu and sigma square also. So here we are having two parameters, right? So we are having two parameters. Okay. Similarly, if I'm having some sort of Poisson distribution, so in Poisson, everybody knows we'll be having lambda as a parameter. Okay, so those things, if we just know this is a Poisson distribution, but we don't know, and we have been given some sort of samples. From those sample, how will we estimate the value of the parameter? Okay, so that is what we'll be going through in whole week 8 content. Okay, like for example, this was the second example of the emission of the alpha particles. Okay, and this is a Poisson distribution, but we don't know the lambda value. Okay, so lambda value, lambda is one of the parameter of this, because we generally have only one parameter in this Poisson distribution. Okay, so in this Poisson, we'll be having only lambda as the parameter. So this sort of parameter will be estimating with the help of our sample values, whatever we are getting. Okay, so now, so what are the parameter? The lambda of this distribution will be some sort of constant value, right? We'll be having some sort of constant for the distribution. But if we are having some sort of like sample one, sample two, sampling we are doing, so I'm having samples one, and we are taking out some sort of values, like for example, if we are having some sort of distribution D. Okay, and out of this distribution, we'll be having some sort of, if this distribution D is having a parameter P, or you can say theta. Okay, so parameter theta is there. So for this parameter, only one, for this distribution, we have only one parameter as theta. If I'm taking out some of the sample, like n sample, I'm taking out from the D distribution for the first sampling. In the first sampling, I'm taking out some sort of n distribution, n not distribution, n samples we're taking. And similarly, in this S2, we'll be taking out some sort of n sample. Okay, so for the first samples, we'll be having some sort of one theta one. This is the parameter first. Not parameters for this samples, we'll be having this parameter that was for the distribution, that is generally constant. If I'm having some sort of distribution, so some sort of distribution is been given. So for this, if theta is fixed, but I'm taking out the samples from this distribution. So for this distribution, I'll be getting some sort of different parameter P, that is P1, or for the second sampling, if I'm doing, we'll be getting some sort of second. So this value will little bit be different from whatever the final, like whatever the constant value we were having for the distribution, right? So for this would be a random variable, right? This would be a random variable. This parameter will be a random variable, and this parameter estimation thing. Okay, so yeah. So this was a Q, that theta 1, theta 2, theta 3, theta 4, whatever. If I am doing the sampling for the n time, n, the capital N times, so we'll be having a n, capital N different theta 1, theta 2. But that will be a much like that theta 1, theta 2, that we have to see, that we have to estimate that theta 1, theta 2 should be as much as closer to the final distribution, like the final parameter of the distribution. Okay, so this is in, so for this, we'll be using some sort of parameter estimation method and all that we'll discuss further. But with this theta 1, theta 2, theta 3, theta 4 can be like, we can estimate, we can generally, this is simply, we can just guess, okay, this theta 1 generally is equals to x1. Okay, this is just simply a guess. But whether this is a correct estimation or not, that we have to check, that we'll be checking further. But we can simply take one sort of distribution, one sort of like random value, because this is a random value, right? So we can just put it like, okay, theta 1 is half for me for all the samples I'm taking out. Okay, so it's a correct estimation, but how correct is that? That we'll be checking with the help of some sort of error, like we'll be calculating some sort of risk, variance, error, and all those sort of things. With the help of those things, we'll be coming to some conclusion, okay, whether this parameter estimating method, whatever I was using, is correct or not. Okay, so there is the second example where the alpha value, that the lambda was the parameter for that distribution, that Poisson distribution. Okay, so for example, we are having a normal distribution with mu and sigma square. So here we are having two parameters. Okay, that for this distribution we'll be using some sort of parameter estimating things for this both the parameter, like for the mu also and for the standard deviation also. Okay. So yeah, so one thing is pretty clear that the parameter is whatever the parameter we are getting for each of the sampling that we are taking out from the distribution will be having some sort of values that will vary each and every time we are doing the sampling. That's why it's a random variable. And that is the random variable will also have some sort of distribution, right? Because if the random variable, the values is varying every time for the samples, that will also be some sort of random variable. That's a normal or a gamma or beta, that doesn't matter, but that will also be a distribution, some sort of distribution. So that from till here we have concluded that but the parameter whatever we are getting will be in the form of some random variable. Okay, parameter for the samples. Okay, but for the distribution will be a constant value. Okay. Yeah, so here it has been noted theta. We are in the whole, we will be denoting this theta cap as the estimator for the parameter theta. If theta is the one parameter, it is the only parameter for the distribution. Okay. So, so now we are with a pretty simple example that if we are having some one Bernoulli distribution with P as the probability of happening and 1 minus P is the probability of not happening. Okay, and we have done this for the n times. So all the x1 till xn is in the form of Bernoulli distribution with probability P. But P here we don't know, it's a parameter and that we have to estimate. So we have just taken three sort of parameters. The three sort of estimator, that is first is half, second x1 plus x2 by 2, and third is a x1 plus x2 till xn upon n. Okay, so this is a three estimator that we are just guessing. Okay, this is the three estimator I'm taking. So in the first estimator, we have just predicted the value of P as half, irrespective of any other conditions. We have just randomly took half as the estimator. P2 also has x1 plus x2 upon 2. But we are having n samples. But we have taken estimator 2 as. Similarly, we can take the other estimator like E4 as x1 plus xn by 2. Okay, similarly, we can take some other estimator also as x1 plus x5 by 5, or anything we can take. Okay, but this all are a correct estimator, but in the end we have to check out whether it's a valid estimator or not, whether it's giving whether the error or the bias whatever we are calculating, it should be as minimum as possible. Okay, so this is what we'll check in the further lectures and all. Okay, so here we are having 5 estimators, for example, this 4, 3, and 2. So out of this, we can directly, like if I'll ask anyone, estimated third is like pretty okay without even knowing many of the things like bias and variance and risk factor and all. Because here all the n values, whatever the samples values are here, all has been used. That's why is one of the, can be considered as one of the best estimator out of this 5. Okay.
Sir,
But
estimator 1 is the best, right?
what?
For this problem, the estimator 1 is like P1 equal to half, so it will be the the ideal value of P.
You can say the ideal value of P, but it's not the, like if we are having some, if we have been given some Bernoulli equation like distribution with P P has not been given. Okay, so
Okay.
P is equal to half you are taking as ideal because you have considered only one thing. You are having some sort of things in the mind, like if this is a condition of head and tail, so P will be half, right? But there can be many conditions where P value can vary from like
Well,
0 to 1, right?
yes, sir. Yeah.
But that will depend upon the number of, like for example, if
For a
I'm
fair toss, like the half will be the yellow P,
yeah.
right?
See, if I'm having some sample, if this is the Bernoulli, right? I've taken out 0, 0, 0, 0, 0, 0, 0, 1. So for this, if you are taking P as a half, this is not a good like guess, whatever you are making the guess for P, right? So if I'm having one distribution, Bernoulli distribution with P as the probability, and when I'm taking out the sample out of this Bernoulli, I'm getting 0, 0, 0, 0, 0, and only one. This out of this, how many? 3, 3, 8. Out of 8, I'm getting only one as the possible outcome, and all the other as a not possible outcome. Okay, so for here, this whatever you are estimating P as half is not a good estimator. It's working, right?
Yes, sir.
Yeah. So that's why that we have to check. Okay, that we have to check from the samples, whatever the samples we are getting, for those samples only we have to predict which we have to predict, or we have to estimate the parameter. Okay, and that parameter whatever we are estimating, for example, this is a sample one, and out of this Bernoulli distribution, this is the sample P1, and for this P1, for this sample first, we are having P some sort of this is a parameter for P. P1 is the parameter for this one. This is not this P1. I'm just taking out some sort of P for some constant, some not yes, for P this for this samples. P4 can be one of the parameter values. Okay. So now, yeah. So this all are the estimator, but now we have to see out of this 3 or out of this 5. Now we have to see which of this 5 or this 3 is the best one, that we have to check. Otherwise we can't say we can't conclude to some sort of values. Okay, so now we have to see how to characterize the good estimator and how to design the estimator. That will see how we'll be designing the estimator. There are methods like MME, you would have read, and maximum likelihood. These are two most used, or you can say ML is the most used estimating design generally we used in the statistic. Okay, so but here we'll be reading two of MME and ML that I'll discuss further. But here we have to categorize which one is the good estimator. For that, we have to calculate the error in the estimation. Okay, so we have to see whether the estimator, whatever the parameter we have concluded, but whether the parameter we have, the estimating thing we have used for that we have, whatever the estimating parameter thing we have used, for that we have to calculate the error value. Okay, so here also, if you calculate the error also, that will also be a random variable. Why? Because this value is varying every time. Whenever we are taking out some sort of n samples from that distribution, this theta cap is varying every time. If I'm doing it for the first sampling, the theta cap is theta 1. If I'm doing for the theta second sampling, the theta 2 will come as sort of theta 2, right? So error will also vary. That's why it's a random variable. And if you have to guess whether it's a if we have to guess whether it's a good estimator or not, we'll be having this see. If this probability value, if the error whatever we are getting, because this error is also a random variable, and this error greater than some delta value, okay, is just going, it's very small. Okay, for if this for one, this some sort of one thing that we can use for estimating whether our estimator is good or not. Okay, so here whatever the error we are getting, whatever the error we are having, already having this theta cap, and theta is simply the parameter for the distribution. Again, theta cap is this the constant value, and this is the variable, random variable for each and every sampling. So if I'm having the probability, if the probability of this error, okay, greater than some sort of, this is a very small value, is also very small, right? Then What does this mean? This means that our theta cap is approaching toward theta, right? Our theta cap is very closer to the theta. If our theta cap is very closer to the theta, whatever the random variable you're getting, if that is very closer to the theta, that means what? This estimator was good, right? If that is very big, then we can say this estimator is not good because we are having some very large sort of noise. Okay, that's why we can't, if we are getting the probability of this error, or you can say probability of the difference of this one, the parameter whatever we have got from the estimator, we have taken some sort of estimator, and from that estimator we have got theta cap, and if the difference between the parameter that we have calculated and from the distribution parameter, the constant whatever we were having, one constant parameter, if the difference between them, the probability of difference, that means the both are very much closer to each other. Okay, if they're very much closer to each other, then we can say that okay, this is a good parameter. If that is the value, the error is not good. If the error is like the probability of that error greater than some sort of smaller delta, is some large value, like for example 1 and all, then we can say this is not a good parameter estimation. It's not a good estimator. Okay, and this then this and anyone can ask like how generally we determine the delta value. So that, for example, the delta value that you have to see ki, how much error you can compute for that parameter, how much error you can give, like for 10% of the statistical error, if you are considering 10% of, or if you are considering 5% of the error, then accordingly you'll get the value of delta, right? For if I am considering the 10% of the data, then delta you can consider a p. If the p was the if the p was the estimator, if p was the that parameter value, then p upon 10 you can consider, if you are considering as 10% of the statistical error. If you are considering 100 100th time, then you can consider p upon 100 as the delta value. Right? This is what has been given. So for this, all the three been in the lecture been like discussed how P3 is the better one while calculating the error. Like for example, we have calculated the from here itself you can see if we are taking out the 10 samples of the Bernoulli, like this was the 10 samples, and from the 10 samples, the P1 is with the help of that whatever the P3 estimator we have defined. For every time the P1 will be constant, right? Because every time we have already taken half as the probability without seeing the distribution, without seeing the samples whatever we are getting. Okay, so this 3 value, every time the first estimator will give half as the value, P2 will give half up and then 1 directly, because this was depending upon only two of the samples whatever we were getting. Like this P2 was what, x1 plus x2, right? x1 plus x2 by 2. So directly we got P2 as 1. So similarly, the P3 was what, x1 plus x2 plus till xn upon n. So here we were getting the here there is a very less variance. Okay, because every time we are getting the value almost similar every time, right? But here we are getting the exactly constant value each and every time. Whatever the distribution, whatever the samples we are taking out, the P1 is every time constant. So this is also not a good estimator, because irrespective of the sample, whatever we are getting, the P1 is always same. P2 is only depending upon the two values. Like if we are having 0 and 0 for the first and second sample, this will give you P2 as a 0. So there is a large variance in this. Like for the first time, if we are giving P1 and if the samples is 0, 0, so you'll get P2 as 0. And for this, if we are having both the sample as 1, 1, so P2 will be 1. So there's a very large variance in this P2 value. Okay, but for the P3, each and every term is getting considered, right? So if each and every term is getting considered, we are having some sort of better like probably, or we can say the estimated value. Okay, so here also we have concluded the same thing. P1 doesn't work for all the values of P. Okay, and P2 varies a lot, because I've seen if the value of the sample is 0, 0, we'll be getting P2 as 0, and if I'm having the sample as 1, 1, then we'll get P2 as 1. So but P3, everything, all the each and every sample is getting considered. That's why it seems to be promising. So here with the sort of example with calculating the probability with the help of some plot, we have also seen this here also for the first estimator we have seen for between this and this value, like upon when the p value is from 5 by 12, in between 5 by 12 and 5 by 9 only, we were getting a bit the error as lesser, right? Or for all the other p value, we are getting the error as very large, right? So it's a simple hit and run. Okay, if I'm taking the p value randomly as 5 upon 7 between this and this value, so I'm getting a better, what you can say, a value of the parameter that is closer to the final or the concluded parameter. But this is simply hit and run. If somebody has taken here, then it's not a parameter, it's a good parameter estimator, right? So similarly for the second case, we have plotted this graph, and then we have came with one conclusion. If the error, when for this probability value, the error is very large, so this is also not a good estimator. But for the last one, if you conclude, if you plot and all, so you'll see this one like is a fairly better one, or you can say one of the best one out of the three. Okay, so till now here I can take one example here. Like I'm having some sort of, see, if I'm having some sort of distribution with x1 is belonging to some sort of, x1 is like x1, so I'm x1 comma x2 comma x3 till xn. So this is some belongs to some sort of random, some sort of distribution. Okay, D, some sort of distribution with theta as the parameter. One parameter, only one parameter for this distribution. Okay. So we can define the estimator E1 as x1 also. This can also be one of the estimator, because we have just asked you which of the fall, like I'm just telling you which can be a estimator. I'm not telling which one is a good estimator. I'm just telling which can be a estimator. That's it. So x1. So for the theta one, I'm just whatever the first sample I'm taking out from the samples, I'm directly telling, okay, this is the parameter value. Okay, the second is x1 plus x2 by 2. This can also be a one parameter like estimator. Okay, PE2. Similarly, PE3 can also be x1 plus x2 plus x3 upon 3. This can also be a one parameter estimator. Similarly, PE4. This includes the summation of all the values upon n. So from here we can see if all the values are getting, so this all four can be a parameter estimator. We are not talking about which one is good, which one is not good and all. So this can also,
so
all
it is A1, right?
Yeah.
P4 will be A1 plus bias.
This is not A1, this is just simply this.
Okay, okay.
Yeah. So this is a P4. So, or we can say, okay, I'm defining this one parameter P5 as maximum of all those values. So that is also a one parameter estimator. That is also estimating the value of parameter only. Whether it's a good or bad, that you have to check with the help of error and all. Okay. So now, yeah, this was one of the example. And if you're having any doubt from the activity question, you can ask. Like till now, like we have discussed till the parameter estimating. We have not went inside how the designing of that. Till there, if you're having any doubt in the activity question or practice or whatever your doubt, you can ask me. Then we'll start with the how the designing part. Okay. Now designing, we'll discuss the error, the bias, error, and variance is also left. Anybody is having any doubt till here? Okay. So now we'll go through the bias, variance, and risk of estimator. Like we were having three estimators, we have taken one was directly we were getting half as the parameter, one was x1 plus x2 by 2, and one is x1 till x summation of all the values of x upon n as the one estimator. But for all the estimator, we can conclude these three things: bias, variance, and risk of the estimator. Okay, estimator. Okay, so for bias is simply how that estimator or the parameter estimated value biased or different from the final or the exact parameter, right? So this is simply, we can say, this is the expectation of the error. This is simply the expectation of the theta minus theta. Here theta is what? Theta cap is what? The value of the parameter that we are estimating with the help of parameter estimator, and this theta is the final value. This theta we are getting from the distribution, whatever the it's given for the distribution. Okay, right? So similarly, like we can calculate simply the bias. There is nothing that we can calculate the bias, but this is one of the important, you can say, thing that will help us to conclude whether it's a good estimator or not. Okay, so this is the one, you can say, one simple formula how to calculate the bias is simply the you have to calculate the expectation of the error. Okay, and this is simply the expectation of error because this is a random variable, so you have to calculate the expectation of this theta. What are the parameter estimator, what are the parameter value that you are getting from the estimator minus theta. This is the constant value for the distribution. Okay, similarly you can calculate the this was the bias. Now you can, okay, so this is the risk, and this is risk is simply the, see, bias was what? Bias was similarly the expectation of whatever the error you are getting, and here we are just squaring that error and getting and calculating the expectation. Why we are doing this? Because many a times what happened in bias, some value can be negative and some value can be positive, and in the end, after doing the summation, we can get a zero. Like we can, that will compensate if some values are higher and some value are lower to some sort of values. Like for example, I'm taking one as the one, that one was the final value. If I'm taking as one as -2 and one as 2, after summation or after doing some sort of calculation, that value, that compensation of those value will be, we can't see with the bias sometimes. Okay, so what happens with the risk, what we are just penalizing, or you can say, if the value of the parameter estimate, from the parameter estimator we are getting a very sort of different value, if we are squaring those error, okay, that can reflect in a better way. That's why we are calculating the expectation of the error. Okay, expectation, we are just squaring the expectation of error so that we can see, we can that those penalized value or the error value can get squared, and we can see it in a better way. In the bias, if that is getting cut down, like if some negative value are there and positive value getting cut down, and if we are getting in the final, we are getting like the value similar to the exact parameter, but the values whatever we were getting from the estimator was not good. But in the final, but the finally we have got the value which are very much closer to the estimator. But we can, if we are getting closer, we can say directly, okay, it's a good estimator, but that was not, because we have seen only with the help of bias. Okay, but if we are taking, if we are taking care of the, if we are doing the squaring of those errors, like if we are doing with the help of, if we are predicting with the help of risk value, then we can say in a better way as compared to the bias. Okay, so now this is simply the risk is simply the, you are calculating the expectation of the error whatever we were having, and that error was what? Error was the parameter estimated that you have calculated minus the parameter value, that constant parameter value. Okay, so now the variance. Variance also you have to calculate the variance of the error, and that variance of the error will be similar, same as the variance of the if you are calculating the variance of the variance of the error will be similar, same, not similar, that will be same as the variance of the parameter that you have estimated. Okay, because see, we have calculated some sort of variance, some sort of error, because in the error what we are doing, we are just shifting the values, right? Because if this was the parameter estimated value, what we are doing there in the error, we are just shifting the value with some values. Like if the theta was 5 here, so every time what I'm doing, the error is what? This is the error. Okay, so if we am taking calculating the variance of this error, this was the error. So to calculate the variance of the error, or you calculate the variance of this theta, this will, both will be similar, because here what we are doing, we are just shifting all the values with 5, right? That's why the variance of the the variance of the parameter estimated value and the variance of the error would be same. That is what has been discussed there. So in the end, we have just came with one conclusion, and you can say it's a important one. Okay, the risk is similarly the B square plus V. Here the risk is what? Risk is simply the expectation of the errors, the squared error. So to B is what? The expectation of the error. We are doing the square of this, and variance is what? The error, the variance of, you can say the error, or you can say the variance of the parameter estimated value. Okay, so till now it's clear. So yeah.
Yes, sir, clear.
So if I have to calculate, for example, I'm taking one question. If I have been given some sort of x1 comma till xn is in the form of some Poisson distribution with lambda, right? And for this lambda, we already know the expectation of this will be what? Will be lambda, and variance is also lambda. Okay, but for this value, if we have been given one estimator as lambda estimator is what? X1 plus x2 by 2. This one estimator that we have taken out, somebody has taken out, okay, this will estimate the value of the lambda, because we don't know the value of the lambda, right? So what would be the value of this? How will we calculate the bias of this? So bias is what? Bias of the lambda, how will we calculate? Bias, we have to calculate expectation of what? Lambda minus lambda. This is what? Expectation of this estimator value minus expectation of that lambda would be what? Lambda, right? So expectation of this lambda cap will be what? Expectation of this one, expectation of x1 plus expectation of x2, 1, 2 minus lambda. So 1/2 expectation of x plus half expectation of x1, x2 minus lambda. So this will be what? Lambda by 2 plus lambda by 2 minus lambda. So here the bias is what? 0. Similarly, we can calculate the variance also. So what will the variance? Variance will be what? If we are having, we have just, so if you have to calculate the variance of this, because we have already know the variance, if you have to calculate the variance of the error, or you calculate the variance of the parameter estimated value, both will be same. So if you have calculated the variance of this one, if we have calculated the variance of this, what will happen? This a will get as a squared 1/4 into variance of x1. So variance of x1 will be lambda by 2, lambda plus 1/4 lambda. So what will lambda plus lambda upon 4 plus lambda upon 4 would be lambda upon 2, right? And if you have to calculate the risk, what is the risk? B square plus b. B we have got 0 square plus b is what? Lambda by 2. So risk will be what? Lambda by 2, right? So till here we are clear.
Yes, it's clear, sir. Now, how do we conclude that this estimator is the best one?
What?
Sir, like from here, how do we conclude that this estimator is the best one? I mean, the
For
estimator
that best one, okay, we'll go further. We'll see how we will.
we have to calculate the risks again, right? Like this way to calculate the risks, and then we have to compare.
Yeah, if see, whenever see risk, you can calculate. See, what was that? Variance and trade. Okay, so risk is what? B square plus b.
Yes, sir.
So just consider this as some sort of constant value. If I have to get some constant value, so if one thing is very big and one thing is very high, that is also not a good, you can say, just think this as a one sort of equation. Okay, this, if we have to get some sort of constant value, if some one thing is will be very smaller, one thing will be very high, right? We have to because we have to come to some conclusion, we have to get some constant value, right?
Yes, sir. Yeah.
Okay, So whenever one thing is very small, the other thing will be very high. So if some sort of estimator, which is having bias also very sort of low and V also very low, okay, all like somehow compromises some sort of things and coming to some sort of conclusion where B, one thing is not very high and one thing is not very low, both are somehow lesser, then we can conclude that this estimator is a pretty good. Okay.
So here, right, you have calculated for the x1 plus x2 divided by 2, right? So if you
Yeah.
take the different estimator and see,
Yeah, you can check with the other estimator and also see that because I am only taken x1 plus x2 as one estimator. We are just discussing regarding the risk. We are just calculating the values, the risk, bias, and variance. If we have taken some other like lambda as x1 plus x2 plus x3 upon 3,
yeah,
or lambda as x1 plus x2 till xn upon n equals to the lambda. That can also be estimated. But which one is good, that you have to check with the help of some sort of error, calculating a bias, calculating variance and all. That
yeah,
you have to, with the help of some sort of information, or you can say that in the end we'll be going through the how biased this estimator is, how consistent this estimator is. Okay, with the help of those you will be concluding, okay, this one, or you can calculate with the help of that what you can say CI also, confidence interval, whether this value is very much closer to our whatever the distribution parameter was not. Okay, with the help of calculating the probability thing also, if that is very much lesser, if with the help of like if I'm considering the parameter as like we can consider 10% of the error, and if with the help of 10% of the error, that lambda, the delta will be lambda upon 10, and then if we are getting some sort of very lesser value, or we can say the parameter whatever we are estimating each and every time, the estimated estimating the value is very much closer to the lambda, then we can consider this is the best one. Okay.
okay.
Like for example, see, if I'm having one lambda as x1 plus x2 by 2, but other as lambda as x1 plus x2 xn upon n, right?
Yes,
From out of this two, you can directly consider this as the better out of this, right?
yeah,
Why this is the better? Because we are having n here, the reciprocal. As the number of the sample will increase, the lambda will get the better lambda each and every time, right? But here will not, here only two samples values are determined in lambda value. So this will not be always be true. This can be true for some sort of samples, but not for all the samples. But this will be getting out of this two, this is the better one, right?
so but there is some the trade-off, right? The uh, number of the size of the n here is less, and here we are considering whole sample.
Yeah, yeah. So if we are considering the whole samples, if we are having n as a very large, we'll be getting n lambda as very much smaller, right?
Yes, yes, yeah,
So in the risk also you have seen ki risk generally comes in the form of 1 upon n terms. So if the n value will be very much higher, or if you are considering n in some sort of parameter estimator, that estimator will be a better one compared to the other. If in the other parameter estimator we are not considering the other. Okay. Then for the parameter estimator, now we have to design the parameter estimator. So how generally we design? We are having generally two methods to design that. One is the MME and one is the ML estimator. Okay. So in that MME estimator, what we generally do? We have, see, generally for all the distribution, we can simply calculate the expectation of that estimator, or expectation of x. We can calculate the expectation of x square also, expectation of x3 also. So all the thing we can calculate with the help, because we already know the formula for the expectation. That is simply the xn, or you can say the function of x, that you have to do the integration. If that is a discrete, you do the summation. Okay. But for in the MME, we have to calculate the moment of the sample. So whatever the sample we have got, we can calculate the moment of the sample. How generally we calculate the moment of the samples? So if we have to calculate the sample for the eighth sample, if we have to calculate the moment of the samples, that is similar to simply 1 upon n summation of all the values of x or kth power, right? 1 to n. This is the moment of the sample. Okay. So how generally we use this moment of the sample to calculate the parameter to help out to help us in the parameter estimating. So if I'm having only one parameter, like for example in the Bernoulli one, we are having only one parameter. For the normal, we have nu and sigma square also. For the Poisson distribution, we are having only lambda as the estimator. Okay. So wherever if I'm having only one estimator, wherever we are having one parameter estimator, we can use the moment of samples for the first order, and then we can like for the moment of sample, we will calculate the moment of sample for the first order, and then we can equate with the x ex. Okay, and with the help of this equation, we'll be able to know the better parameter estimator. Here, like till now, what we have, we were just using some sort of parameter estimator hidden with the hidden parameter. Just we were considering p1 some sort of parameter estimator, and then we were doing all the other things. And then out of those parameter estimator, whatever we have, whatever the we were getting in the mind, we were just putting this. Okay, this is the one first parameter estimator, this is the second one, and out of those we were selecting the best. Here now we have started designing the parameter estimator. So how will we design? This was the first method, moment of the samples. What we have did. So this was the simply this is the moment of the sample. This is the distribution. You can say the moment of the distribution. Okay, that we are equating both the equating, and then with the help of equation, with the help of some examples, I'll let you know how generally we calculate the moment of the sample. So how this is the one formula that you should keep in the mind. How generally you calculate the moment of the sample. If you have to calculate the moment of the samples for the kth order, we'll just do 1/n summation of all the if you have to calculate for the kth order, you'll just what you can say, you can just kth power of all the samples value, do the summation and just divide it with the n. You'll get the m1. Like for the m1 is what? M1 will be simply all the summation, all the values of x upon n. For m2, what will be the value? Summation of 1 upon n, summation of x I square. M3 xi 3 upon n. Okay, so these are the m1, m2, m3. And if you have to get, say, expectation of, if we have to calculate, if we have to get the parameter estimator for for the parameter, whatever for the parameter of your distribution, you can just equate e2 with e2. If you are having only one estimator, or if you are having only one parameter, you can just calculate and equate it with the e1. And with the help of these equations, you'll be able to know the parameter estimator. Like for example, I'm telling one example. Like I'm having one gamma distributed x1. This is a gamma distribution with alpha beta, right? And for the gamma distribution, this moment for this is the moment for the distribution. This is what? Alpha by beta, and e square is what? Why I'm writing this ex and e square? Because we are having here two parameter, and for the two parameter we have to get the parameter estimator. Okay, so for this, for the expectation of x, we are having alpha by beta, and for the expectation of x square, we'll be having x square by beta square plus what is this? Alpha upon beta square. Okay, this has been given to you. Okay, now we have to get the parameter estimator for alpha and beta. We can just put any values in the like parameter estimator, but those are not like, again we have to see which one is good and not. But here we are just designing the parameter estimator. Okay, so what we'll do, we have to use the moment of samples. For the moment of sample, how will, for the two, if we are having two parameters, we'll be calculating m1 and m2. Okay, so m1 is what? M1 is the expectation of x, that is similarly the x summation of all the values upon n. This is what? Expectation. So m1 is what? M1 is alpha upon b, right? M2 is what? So here from here we can, this is the first equation. This is the way I'm telling you how to solve this equation. So alpha can be directly, alpha is what? Beta m. So you can put the value of alpha here, beta m1 ka whole square upon beta ka square plus beta m1 upon beta 2 is equal to m2, right? So beta square will get cancelled. So we'll be having with m1 square plus beta will get cancelled. We'll be having m1 upon beta is equal to m2. Right? So now you have to solve, you have to get the beta from here. So alpha we were already having. So m1 upon beta, what you will get? m2 minus m1 ka square. So m1 upon m2 minus m1 ka whole square is equal to beta 1. Right? So you have got the parameter estimator for the beta. Similarly for the alpha, what is this? Alpha is what? Alpha is simply beta into m1. So beta is what? m1 ka whole square upon m2 minus m1 ka whole square. So now you have the both the estimator. What is the both the estimator? So here you are having the estimator for the alpha. You have, what was that? For the alpha you are having m1 ka whole square by m2 minus m1 ka whole square, and for the beta you are having m1 upon m2 minus m1 ka whole square, and m1 m2 you already know. What is that m1 m2? M2 is what? The summation of x ka whole square upon n, and m1 is summation of x upon n. Right? So this is the for the parameter estimator of alpha and the parameter estimator of beta. And you got some point? Okay, so this is the one method to calculate the, to get the parameter estimate. So this is one of the good method to calculate the, this was the MME method. The second one is what? ML method. So MME method, everyone is clear?
Yes, sir.
For example, I'm having, so for MME method, one more question I'll discuss here. So if I'm having a distribution as okay, this is the distribution. Okay, I'm having that x value will lie from -1 to 1. For this value, you have to get the parameter estimator for theta. Here only we have only one estimator for this distribution, right? So what we can do, we just need m1 here. M1, we just have to calculate with the expectation of x. Okay, from here we'll get the value of m1. We'll get the value of the, we'll get the estimator for theta. So what we'll do? Expectation of x, how we'll calculate? Expectation of x is what? 1 upon theta x by 2 into x. We have to do the integration we have to do. This is not x, this is multiple of x from -1 to 1. So 1 upon 2 can be here. So x square upon 2 plus theta can be x cube upon what? X cube upon 3 into 1 upon 2, right? Will be equals to m1.
Yes, sir.
Right? That we have to put -1 to 1. If we'll put the value of minus from if we put the value of x, so what will be the value? 1 upon 4, x is what? 1, minus of minus, that will get cancelled. So this will get cancelled. And now we'll be having 1 upon 6 cube, 1 minus of minus 1 का whole cube equals to m1, right? So q will be what? This will be 2, sorry, 3 m1. So this is the one parameter estimator for this q, and that is 3m. M1 we already know. M1 is what? The summation of x upon n, right? So this was the first MME method. Now we'll go to the ML method. So this is simply the maximum likelihood, what you can say, maximum likelihood estimator. So here what we have to get, first we have to get the likelihood function. Okay, and then for that likelihood function, whatever you will be getting, you have to maximize those. And for maximizing those, we'll get the for what at what point or for what parameter you'll be getting the maximum value of this likelihood function. Okay, that is what generally we do in the maximum likelihood function, right? So how generally you calculate the likelihood function? So likelihood function is what? Simple. Like if you are having some sort of examples, like I'll go through the lecture. So if I'm having yeah, so what is that maximum likelihood? We have to just first we have to see what is likelihood of the samples. Okay, so if I'm getting some sort of this, so here in this example we were having one distribution, and for that distribution we were having like q1, q2, q3 till n, whatever the value the q1, these all are the parameter that we have to estimate. Okay, and fx is the simply the PDF, or you can say PDF if that is a continuous, and PMF if it's a discrete. Okay, so for the likelihood function, what is the value? The function of likelihood is the probability of happening of that sample. Like if I'm having the sample as x, this is the sample likelihood of the sampling x1, x2. If I'm getting this as the sample, right, x1 till x, if I'm getting this as the x1 till x, then that will denote the what is the likelihood of this. Likelihood of this means what? And for the x, what are the function? X1 multiplied with x2, because we have to get the probability that this sampling is happening. Okay, for this sampling is happening for all the x1, this sample. Okay, for this sampling, what is the probability? So for that we are calculating the likelihood function. So fx1 into fx2 till fxn. This simple likelihood function. Okay, so now we are already know the likelihood function of the equation. If I'm getting this sample, if I've done the sampling once and we have got this as the sample, and for this sample we have to get the likelihood function. So we have got this as the likelihood function, right? Okay, so this is the likelihood function for us, right? And for this likelihood function, now what we have to do, like for example, we were having one normal distribution, and for that normal distribution, we got x1, x2, xn, all the x till xn as one of the sample. When we did the sampling, we got this as a sample. And for the sample, we have calculated the likelihood function was just multiplying all those probability value at each point, right? So we have done simply, we have just multiplied all the value. Like for example, we are having a Bernoulli distribution, and for that Bernoulli distribution we have taken out one sampling, and in that sampling we have got this as the sample values. For this one we have just written what is the likelihood function for this. If I'm having Bernoulli distribution, and with the Bernoulli distribution, if I'm having the Bernoulli distribution with P as the parameter, the probability, and we have taken out one sample, we have done one sampling, and we have got the samples as 0 1 1 1 0 1 0 1. Okay, for this if you have to calculate the likelihood function, that means what? Likelihood for this sample is what? But P will be writing 1 minus P into P into P into P into 1 minus P into P into 1 minus P into P. Okay, so this is the likelihood function that we are getting for this Bernoulli distribution if we have taken out this as a sample in one sampling, right? This is what has been written. Okay, so for this sampling, or you can say if you are taking out the normal distribution, and if this was the norm, if this was the your sample, then for those values, all you have to what you have to put, you just have to put in spite of x, you have to put this and multiply that with the other samples, whatever you're getting. So simply likely is what? Whatever the probability value, if you have done one sampling, and for those all sampling, for that sampling, whatever the samples you are getting, what is the probability that all those sample will happen? Okay, so for what you will do, because each of the sample is independent of the other sample. Okay, so we can just multiply those value to get the likelihood function. So now what we have to do, we have to maximize those values. Okay, we have to maximize that function. Okay, for maximizing those function, if we have to maximize those function, right? So maximizing those function, like this was the likelihood function for us, this was the likelihood function. Okay, and for that likelihood function we have to maximize those likelihood function. And if I'm, so this is simply a optimization problem we are having. So this is a distribution we are getting in form of q1 and q2, right? In form of q1 and q2, q1 and q2 you are getting. What you have to do, you have to get, you have to maximize this value, and argument of this means what? We have to get the q1 and q2, the best q1 and q2 where the value of this will be maximum, right? So that is simply that you have to do in the MLE. So you have to first, the step is, first step you have to calculate the likelihood function, and second you have to just maximize this, maximize that, and you have to get the value of q1 and q2 where the function is maximum, right? For that what you can do, see, this is simply a product of all those functions. If you are having, if I'm having one function in the form of product, what we can do is to just simplify that. We have just taken the log. Okay, we have just taken the log, so that whenever we'll do the whenever we have to calculate the, we have to, whenever we have to estimate the parameter with the help of some differentiation, like how generally we calculate the maximum value for any of the equations. Generally, we differentiate and then equate to zero, and the second differentiate, the second variable generally gives us the maximum minimum value. But here we are considering whenever we are doing the whenever, but here in most of the question, the optimization problem will be in the way such that you have to just differentiate with the respect of the other unknown, or the you are estimating the parameter. You just have to differentiate with respect to those unknown parameter, and then equate it with the zero. You'll get the maximum value at those points. Okay, so just you don't have to like think about what would be the second derivative and all this stuff. So here it has been considered whenever you are just differentiating with the help of differentiating with respect to the other parameter, whatever the known parameter or whatever the parameter you are estimating, you just have to differentiate with respect to that, and then you have to equate to zero, and you will be getting the estimated parameter estimated, like the maximum likelihood estimated you'll be getting. Okay, so what we have did, we just did. Okay, so for example, if I'm having this as the Bernoulli with the P, Bernoulli with P. Yeah. So if I'm having some Bernoulli equation, Bernoulli with P as the parameter, right? And with the help of MLE, we have to get the parameter estimator. So one method is that we can use MME method also, and one is that we can use ML method. So here we are using ML method. Okay. So what we can do here, if for example, if I'm having some sort of sample, so x1 till xn. Okay. For this sample, we can calculate the likelihood function, right? What will be the likelihood function for this? For example, out of this x1 till xn, we have got, out of this n, we have got some sort of w1, and the rest n minus w is 0. So what we can do? We can just multiply the pw times, and we'll be just multiplying 1 minus p as n minus w times. This is our likelihood function, right? And now we have to maximize this, and we have to get the estimator, parameter estimator. Okay, so how can, so if we have to maximize this L function, maximize this function or maximize this taking the log of the, why we are taking the log, just to simplify this, nothing else. So if anybody has any confusion why we are I'm taking log, whether it will change the value of p and w, so you can ask. So generally it will not change the value, because see, logarithm is simply a decreasing function, increasing function, right? So if I'm taking the log of this function, if I'm taking the log, that will help us, and this multiplication generally will get converted into the addition, and then we can simply we can do the mathematical operation in a simpler way, because in the multiplication we're not able to get. So that's why this optimization problem will solve by taking the log in both the terms. If I'm taking the log, it will get simplified, right? This will be p plus n minus w log 1 minus p, right? And then we can just differentiate this function, log function, with respect to L, and then with respect to p, and then we will get some parameter estimator, right? Like for example, if I am differentiating p, what will the value? N minus w by 1 minus p equals to 0. Right? So here also it will be minus, because log, if I'm doing the differentiation with respect to p, 1 minus p minus, and we differentiate. So w by p will be equals to what? N minus w by 1 minus p. So w minus pw equals to what? Np minus pw. So this will get cancelled. So p will be what? W upon n. And we have got very good estimator, right? How generally we can say this is a good estimator? Because see, probability generally in the Bernoulli, but with the probability. How many times we have got the 1 upon all the number of samples, or on the number of samples, right? So out of that sample, if I'm having 10 samples, out of that 10 samples, if I'm getting 4 as 1, so the best parameter, the best probability would be what? 0.4, and that is what we are getting here. So W is what? How many times we are getting 1, and N is the total number of samples in that sampling, right? So here we are getting W upon N. So this is one of the best parameters estimated with the help of MLE here, right? Similarly, we can do for the Poisson also. See, for the Poisson is what? We have to estimate lambda. And how we can write e to power minus lambda. How we can write e to power minus lambda. In the Poisson, we can directly write e to the power minus lambda, lambda to the power xi upon xi factorial, right? And if we are getting the samples x1 till xn, so we'll just multiply, we'll just do the product of all xi from x is equal to 1 to n, right? So this is the likelihood function. If I'm taking the log of this likelihood function, this will get converted into addition. This will, so what we'll get? We'll get the xi, what, x1, x2 till xn, right? E to the power, this will get multiplied n times n lambda, and if we are multiplying lambda to the power x2, lambda to the power x3, so this will be in the form of summation. Summation. Right? If I am taking the log of this all values, what will happen? What will happen if I am taking this can n lambda log e? This will be what? 1 plus this x1 xn log lambda, right? And now you can differentiate. Now you can differentiate with respect to lambda. So if we are doing the differentiation, what you'll get? Minus lambda plus this summation of x upon lambda.
Yes.
Sorry, here it will be 9.
Yeah.
Right? So now we can just n equals to summation of x by lambda. So lambda is what? Summation of x by n. This is the one parameter estimator you got from the ML. Right? So similarly, you can do for the normal distribution also. If you're having normal distribution with mu1 sigma square, so you can just write the distribution. If you're having the some sort of samples, you have got xn likelihood function, you can write in the form of mu1 sigma both 2 pi sigma. If you are doing the multiplication, if you are doing for all the samples, you'll just get multiplied n times because this term will come every time, right? And with the expectation, what is that? 2 sigma square x1 minus mu ka whole square. Every time it will come, so it will go in the summation part, right? Okay, again you can take the value of log, and if you have to calculate mu to differentiate with respect to mu, take this as a constant. You'll get one estimator for the mu, and if you have to get the estimator for nu square, take this as a constant, keep this as a constant, and differentiate with respect to sigma, and you'll get the parameter estimator in the form of parameter estimator for the sigma, right? Are you getting the point? Or everybody is sleeping, I guess?
Yes, I get it. So, like,
Yes, sir.
out of these two methods, like, which one,
What?
out of these two methods, like ML and the other one, like,
Yeah.
which one have to use? Like, try to use.
ML, every time you should use ML.
Okay.
I'll do the comparison for one example. Okay, so now I'll do the comparison for one example.
Okay, so,
See, problem is what? If I'm having some distribution D, right? So x1, comma xn all belongs to D. Okay, and here in this D, all the samples can be 1, 2, or 3. Right? So the probability of getting 1 is P1, getting P2 is P2, and probability of getting 3 is 1 minus P1 minus P2. Right? This is simply a distribution, some sort of distribution, where we can get the samples, 3 samples we can get, 1, 2, and 3 we can get. 1 we can get with the probability P1, 2 we can get with the probability P2, and 3 we can get with the probability 1 minus P1 minus P2. Right? So now what I'll do, I'll just calculate or I'll estimate the P1 with the help of MME, that's the moment of sample, and we can do P1 with ML also. So I'll do P1, P2 with both MME and both the thing. Right? So first is MME, or you can say the moment of samples. So moment of sample, how generally we calculate moment of samples? So we generally equate M1 with expectation of X1. The expectation, how we'll calculate? P1 into 1 plus P2 into 2 plus 1 minus P1 minus P2,
Plus P2.
3, right?
Yeah.
This is the M1. M2 is what? P1 into 1 plus P2 into 4 plus 1 minus P1 minus P2 into 9. How we have done? This is simply M1 we are equating with what? Expectation of X, and this we are equating with expectation of X square, right? That is what we have learned to calculate the MME,
Yes, sir. Yeah.
right? So what we'll do, we just have to somehow solve this and come with like, we should be having P1 and P2 because we can get the P1 and P2 in terms of M1, M2, because M1, M2 we already know. M1 is what? Summation of X upon N. M2 is what? Summation of Xi whole square upon N. That we already know. Yeah. So this is the equation. How we'll solve this? We have to get in the form of P1, like we have to get P1, P2 in the form of M1 and M2.
Sir, can you help me one thing, sir? Actually, if it would be better if we could do some activity question based on this ML and ME comparison, because I was figuring out, I was unable to. Activity question 8.8, 1 and 2, if we could do it, it could help us both, sir, comparing both and
Okay.
learning also side by side simultaneously.
Okay, then I'll open it. Okay. 8.8, right? So almost we have covered everything. Nothing is only CI is left in the conceptual wise. Everything else has been covered. So now we can go to the activity question also. Which one you are telling? 8.8.
Yes, sir. 8.8, question number 1 and 2. It is same question, sir. One is carried by ML and second one is MME method of both the methods are. Yeah,
This
1 and 2. Yeah, both are.
okay. So see ML you can directly, okay, I'll write it here. So what I'm having X equals to 0, 1, 2 and 3. 1 with the probability 2p upon 3, 1 with the probability p upon 3, right? 2 with the probability 2 into 1 minus p, 3, 1 minus p upon 3, right?
Yes, sir. Yes.
So this we can calculate with the help of ML and MME also. So how many times we are having X equals to 0? So the samples, whatever we are getting is what? See, the samples we are getting is what? 3, 0, 1, 2. So how many times we are getting?
Total sum is 14, sir, and 9 times. N is 9.
Yeah, N is 9. So how many times we are getting 0?
2 times.
2 times we are getting. So we can directly write it here. 2p upon 3 to the power 2, right? So
Yes, sir.
first we have to calculate what? Likelihood function. So we are just getting the likelihood function, and then we can take the log and differentiate with respect to p, so that we can get the parameter estimator for p, right? Are you
Yes,
getting
sir.
it? Yeah.
Yes, yes.
How many?
So for this, when we do differentiation, actually, sir, if it is of normal, say, square power, okay, sir, no issue. But as you could see, sir, this one, this power, it's going a bit large.
Okay, I'll try to what you can say simplify that. So one, how many times we are getting? 1, 2 times, right?
Yes, sir, 2 times. So p by 3 whole square.
We are getting 3 times. Sorry, p upon 3 cube, right? How many times we are getting? 2, 2 times.
Yes, yes.
Sorry, 3 times. 1, 2, 3. So
Ah.
2,
different from mine.
3 times.
Sir,
Yeah,
actually, one, 2 times in my question. Okay, it's differing. Okay, it's differing.
yeah.
I
And
don't know.
then
There must be some glitch, sir. So for mine, it's showing only 1 2 times and 0 2 times, 3
yeah,
2
the
times.
samples would be different for everyone. Yeah.
Okay, okay.
So now I'm getting, so 3 plus 3 is what? 6 plus 2. So I'm getting 1 minus 3 upon 3. 3 how many times is there? 2 times, right? So 2. Now take the log of this. So whenever you will take the log, what will be the value of this? Log 2p upon 3 plus 3 log p upon 3 plus 3 log 2 1 minus p upon 3 plus 2 log 1 minus p upon 3, right? So this is the log of n, log of L. Now you can directly differentiate. So what is the issue here? You can differentiate it, right, directly. 2 into 3 by 2 p into 2 by 3 plus 3 into p by 3 into 1 by 3. Similarly, you can do, and then you can get the p. Equating with 0, you will get p some constant value. Right? But are you getting my point? Okay. So similarly, you can do for the MME also. What do you have to do? You have to calculate the expectation and equate with M1. Similarly, calculate the for the x square, equate with M2. You'll get P here also. Right? Any other questions you want to discuss? Whoever was asking is clear now? Hello.
Yes, G. Yes, yes, yes.
So what is the other question you're asking?
Only these two.
Oh, okay, okay. So anybody else is having any other doubt? Like, so why conceptual? We have already discussed all the points. So only that confidence interval is left now. Okay, so we'll go to that confidence interval. So see here it was whatever I was discussing in the last, like, what is that? Yeah. So here this example only I was discussing. So when we were having the problem in the form of P1, P2, P3, we got to know that whenever we were estimating the P1 value, we got the P1 in some random form, like 3 minus 5 by 2 up into M1 plus M2 by 2, where M1 is a summation of X1 N and M2 is summation of X whole square, X1 square, summation of all the X1 whole square upon 2. But when we have calculated the same thing with the help of ML, what we have got? W1 upon N, where W1 is the number of times one is occurring. So this is you can simply say with the help of ML, maximum likelihood, you are getting a better estimator for P1. Why? Because here you can see P1 was some random things, 3 minus 5 upon 2 M1 plus M2 by 2. But here what we are getting P1 as W1 upon N, where N is the total number of samples, and out of that total number of samples, how many are 1 exactly? Okay, so this is the best one. When how you are calculate the probability simply? You calculate the probability number of times something is occurring over total number of occurrence of the samples, right? So this is how, this is the best parameter estimator you got from the ML. So ML generally gives you the best, you can see the parameter estimator. So simply for the ML, for the second or the parameter for the P2, you have got W2 upon N. W2 is what? The number of times 2 has occurred upon N. N is the total number of samples. Similarly for 3, you'll get the total number of times you have got W3 upon N. If you have to estimate the 3. Right, so ML would be a better estimator. Similarly, you can go through the lectures for the uniform distribution also, gamma distribution also, binomial. Everything has been discussed here. Now we'll go through the what you can say conditions, confidence interval. So, for example, you would have went through many. You would have went through some sort of data like here. Here there has been given 95% confidence level with a margin error of 3%. That means what? So the probability of the error less than whatever the 3%, less than of 0.003 of p is equal to 95% of the, or you can say 0.5. Sorry. So if you are having some sort of, if you have been written, if you have got some information and it's been written in the form like 95, like some sort of like 80%, because Indians are willing to take the vaccine and the sample values or the sample is very small, that is of 3045. Okay. And then you have been told that 95% confidence level with the margin of error is 3%. Okay. That means the probability that the error is less than 3%, probability that the error is less than 3% of the probability, okay, 0.03, or you can say alpha is equal to what, 95, or you can 0.95 of the beta, or that will, okay. This is what generally tells us ki the value, this is the form of mod. Okay. So 95% of the confidence level with a margin of error of 3%. That means what? The probability that whatever we were estimating is 95%. The probability that will occur between some sort of information. For example, this, if we are having some sort of mu, if mu was the parameter estimator, okay, so mu plus 0.03% of the mu. So mu will lie between 0.03% of the mu with 95%. Okay, so mu will lie between this two value. If mu cap you were estimating, so mu minus 0.03% of the mu. So this mu will lie in between this with the 95% of the probability. That is what generally tells this information. Okay, so whenever you see this type of information, 95% of the confidence, so it's telling the probability of occurrence of this mu or whatever we were estimating, occurrence of this in between mu minus 0.03 of times of mu to mu plus 0.03 times of mu is 95%. Okay, right? So here it has been given. So probability of the error or the probability of the parameter estimated, whatever we were estimating, less than point, or we can say the 3% error was there. Okay, the probability that the mu or the whatever the estimating parameter, whatever we were estimating, will occur between mu minus 0.03% of the mu plus, like in between mu plus 0.03% of the mu and mu minus 0.03% of the mu with the 95% of the accuracy. Okay, if it has been given 99% of the 99% of the confidence, well, you can say the probability that the mu is occurring between these two values would be 99%. But if you consider this margin of error as 1%, so you have to get, you have to tell, okay, the probability that the occurrence of this mu between this here, the if you are considering as a 1% of the error, then it will become 0.01 to the 0.01, and the occurrence of this in between this is 99%. Some sort of things like that. Okay. So this was the confidence if you have been given this sort of like example, 95% of the confidence intervals, that simply generally means that the probability that the estimated value lie between these two values is this much, 95% of whatever the value it has been given. Okay. So that is simply you can say the mathematical equation. If you want to write the x minus mu less than alpha, will be simply this one. This mu is lie between this minus alpha, this mu minus alpha to mu plus alpha with some sort of confidence interval, some sort of probability like 95%, 98%, or whatever you are thinking. So in the end, like one sort of example is this. Okay. So if I'm having normal samples with the known, so there can be the two conditions where we are doing one of the, if I'm having normal distribution, okay, if I'm having the samples in the form of normal, we are taken out from the sample, if I'm having the samples from a distribution that was normal. So normal distribution generally have two unknown, two parameters. And out of the two parameter, if we are having some sort of, if we are knowing the parameter, like if mu is unknown, and we have to get the parameter estimated for mu. Okay, the estimator, like for example, we have taken out this as a one estimator. Okay, x summation of x, and we can take out with the help of some MLE method. Okay, so we have got this mu as x summation of xi upon n. Right, and nu the sigma square by known, so we can get mu with the help of ML directly. Okay, now what happens, but if now we have to give the confidence interval also with the help of some margin, like as I have discussed, like with some sort of point like 5% or 2% or 3%, we have to give some sort of information like that. Then what we will do, if I'm having the estimator, we have got the estimator in the form of this summation of xi upon n. So if I'm this mu, whatever the parameter estimator, that is in the form of normal distribution with sigma with mu and sigma square upon n. So that can be randomized. That can be, we can convert this mu upon sigma, because this again with the if I have to calculate the probability, anything in the form of normal with mu upon mu comma sigma square upon n, that will be a very painful, because again we have to write all the equation like 1 upon root 2 sigma on with the help of those bigger equation. We have to calculate the probability value. So it's better we can directly convert that normal distribution. We can just shift the mean to the 0, and we can standardize that normal distribution. So now we'll be having mean as 1 and sigma as equals, mean as 0 and sigma equals to 1. So for that, what we can do, we already know in the last the last what do you can say week also, we have went through that how generally we convert that normal distribution to a standard one. Okay, where the mean value will be 0 and the sigma will be 1. So how we can do, we can directly do with the help of, this is the sigma square upon sigma, like generally we do x minus sigma upon root n, right? So here also we did the same thing. We have just divided this with the sigma upon root n, and every time we'll do the same thing whenever we have to calculate some sort of information. Okay. So now we have got this one. So probability of this error, or the probability of the error from the probability of the estimated probability of parameter estimated parameter from the given mu is less than alpha, and alpha is similarly alpha is that you can say the delta value, or you can say the margin of error value equals to beta, and beta is the confidence level you'll be getting. So I'll discuss, I'll take one examples from the activity question, and then we'll discuss, maybe that will clarify. So with the help of this standard normal, we can standard normal distribution like Z distribution, that formula, so you can calculate the value of beta, and then you can get the value of probability or the confidence level. Okay, so if we are in the same way, if we don't have, if both of this value, if the mu and sigma, so both of them are not available, then you can use the T distribution. Okay, and then with the help of T distribution, you can calculate the confidence interval. Like for example, this is the example, like I'll take one example. Like here we are having 100 samples are drawn from the normal distribution mu1. Here mu is like this other one, the sigma is known. So now we can directly use the normal distribution. We can normalize. We have just have to normalize this. We already have the sample mean at 85.7. So okay, I'll write it here. So now we already have what? So the sample n was what? 100. We have to do it for the confidence interval of 90%. We have to get the value of the whatever the estimated value was what mu. We have to get the interval where the confidence. So we have to get the interval of that mu estimated, so that whenever we'll take out them some sort of samples, the estimated mu or the estimated mean of those samples will lie between this two, so that the confidence with the confidence of 90% we can say that. Okay, and sigma is what for this? Sigma was 4, so it was normal with sigma and 4 square. And mu it was given as 85.7, right? And this was the sample mean. Right? So here, okay, so this information is very much useful to us because this is what generally we have to calculate the alpha, right? 1.64. So just alpha upon what? Sigma by root 10. That is equals to what? 1.64, or what was the value? 1.64. From here we can get directly alpha 1.64 into sigma upon root 10. N is what? 100. So 1.64 into sigma 4 upon 10. So you'll get some value alpha here. So alpha you'll get some sort of 60 into 460. You'll get some alpha here. What is that? 16 into 464. So 0.64 upon 10. So point, yeah, 6.4 upon 10. So you'll get some sort of 0.64. So it's close to 0.64. You'll get close to 6.64, right? And now, so now sigma you already have. So what you have to calculate? So you already know the value of alpha, right? So mu minus alpha and mu plus alpha would be the interval where you can say the estimated value of mu will lie between with the estimated value of mu will lie between this value with 90% of the confidence, right? So what you don't have to do anything, just whatever the value that will be given, you just have to compare those values, get the value of alpha. Alpha is similarly the margin of error that you can get, and then you can just write it like this, and then you will get the interval. You'll get the interval in which the mu or the parameters, the estimated mu will lie with this 90% of the. If that is was 95, we'll get the other beta value that you have to equate with that beta value. You'll get the alpha there with the corresponding beta, and then you can directly write the interval, right? So all the concepts can be discussed. Now if you are having any questions from the activity or practice and all, you can just ask. Otherwise, anyone, like, are you listening, or like everybody has left?
Yes, sir.
Okay, then if you are having any doubt, you can ask from any activity or any practice. Otherwise, we'll close the session. Does anybody has any doubt or any questions? Am I audible or not?
You are audible, sir.
Okay, so does you have any doubt or not?
So no doubt from my end.
Okay, so okay, if you are having any doubt, you can ask. Otherwise, we'll close the session. Okay, then thank you, everyone. You can leave the
Thank you
call
so
now.
much, sir.
Yeah, thank you.
Thank you.
Yes, sir.
Thank you, sir.
Yeah, thank you.